It's shower.
Very happy to see you here, and thank you for dedication to the class, voluntary or involuntary. So, 50 slides for 40 minutes or something like this. Last meeting, I don't know if anyone was watching recordings, was ordinary. This one will be for you as well. So you didn't miss the whole message.
Perfect.
Too many things. Maybe I will just start quickly mumbling everything I have in plan, but generally, physical chemistry, expected outcomes of the instruments, wavy properties of electrons, vibrations, and rotations, right? That's what we do here. And now we are focusing mostly on rotations. If this day will be successful, if I will be able to compress everything in the right amount, today will be a triumph of science of beginning of 20th century. If today's lecture will be delivered in, say, 1910, then each of you will be able to get a Nobel Prize and revolutionize the world science. So we will continue looking on the rotations, primarily focusing on rotations of electron and of nuclei, although this approach is rather general. And last time, for about 2 lectures, we were imposing chains and constraints on ourselves and our ability to do a lot of things. We were constraining rotation in plane, and we were constraining rotation to a rigid distance between these two masses, right? It was rigid order. At the end of last lecture, we slightly deviated from planar rotations and saw consequences. There will be degeneracy. Today, we will break one more chains of restraints. We will allow expansion and contraction of the distance between rotating objects. There is no time to do everything rigorously in all tiny details, but we'll get sufficient principles so that you feel comfortable and, if needed, make next steps toward yourself. So, the ability of rotating objects, primarily electron and nuclei, is the core of atomic spectroscopy. Is the core to answer why atomic spectra have linear shape rather than continuous. And the following sentence is very standard, and I'm compressing it, but in many courses one speaks like 1 or 2 lectures. One says classical principles of motion, then electron moving around nuclei will continuously fall down on nuclei and irradiate electromagnetic radiation in all ranges of frequency with continuous spectrum. And experiment tells otherwise, so it is very sharp points. And approach of today will explain why there are sharp lines with sufficient amount of truth and acceptable approximations. Is it sufficient for an intrigue? Okay, start, set, go. Okay, John is not, it's my lack of luck. Today John is not here, but everyone else can skip it. Angular momentum is quantity of motion. If they are vectors in 3-dimensional, it is cross product. And if one does cross product in elements in Cartesian projections of momentum and distance, one will get three elements of rotation. And if one carefully opens the determinant of this cross product stuff, then there will be x, y, and z projection. And z projection of angular momentum by the rule will be position times momentum in y, position in x times momentum in y, position in y times momentum in x. Right? And if John plans to continue his choice in the project, LZ is a product of one-dimensional operator of position and another one-dimensional operator of momentum, but they are in different dimensions. Okay. I'm trying to arrange stuff, but you already know your choices. And this is what we did last time. So we quantized angular motion for rigid rotator, found that it has the shape of exponential with angle, azimuthal angle in the power, and the values of angle are multiplied by discrete integer numbers. And then we studied the degeneracy so that one gets the same energies with opposite direction of rotation. And then if we practice the same thing for two-dimensional rotations, when there is an opportunity to go outside of the plane, then the degeneracy is more than two, like 1, 3, 5, 7 progression, which are SPD orbitals. And this gives, I'll tell you when to wake up and focus really strongly. And this gives rotation vibration spectroscopy, so energy offset between levels, occupations, and matrix element, which is similar to oscillator frames, and it imposes the selection rate. So this hump has two, it's symmetric and it has two trends. So the offset is because of the specific energy differences between these discrete levels. Increase of the intensity is because degeneracy grows as far as you go to the higher energy. Decrease in intensity because when you go higher and higher in energy, the states are less and less occupied. It is because of the Boltzmann distribution, thermal distribution, which will be main focus of TChem2. So this factor is like degeneracy grows, and the thermal distribution decreases. So these two trends are responsible for intensity. So if things go well, we will have this slide plus a couple of more entertainment slides. Okay. We are on a straight path. One of the few equations that you may want to remember independent of your career, even if you are going to be very far away from science, is this 1 over integer squared. Please give me a little science if you have an idea what this equation corresponds to. And do not hesitate. If you tell wrongly, there will be no consequences. So, hydrogen atom.
Quantum state of H orbitals.
Yes. I'm slightly wrong with notation. Typically one uses the letter N, principal quantum number. So the orbitals, atomic orbitals in hydrogen atom have specific energies. Right? And one can establish correspondence between number of orbital, its shape, and its energy. This is a feature of nature, and this can be obtained approximately with Bohr model, more precisely with Schrödinger equation, and there are some additional corrections if one looks for like 7th digit with something on the top of the Schrödinger equation. So though this 1/2 1 over s squared is n principal numbers, the energies of the hydrogen atom orbitals. For s orbital, it will be just minus 1/2. Minus 1/2 in which units? Yes, perfect. And then if one goes to the excited state, it will be higher, right? So minus 1/8 is bigger than minus 1/2. And then they will keep raising, but their offsets will be smaller and smaller. Okay? So this was a big barrier in development of science at the beginning of the 20th century, because everything that was working for other systems was failing here. And it was a little revolution that Bohr's model helped to overcome, and then the Schrödinger equation helped to be a little more precise. So we are going to arrive to this conclusion. What are the lines in here? Any ideas? From
Activation energy.
Good try. Okay, what is on X and what is on Y?
Position energy.
Position of what?
Electron.
Yes, but electron is three-dimensional object. Distance from.
Oh, the nucleus.
Huh?
The nucleus.
Yes, yes, distance from nucleus. So suppose that we forget about rotation and just look how it is attracted or repelled. What is the interaction between electron and nuclei? Do they feel each other or they do not care about each other? Electron and negative electron and positive proton. Right. Why? Who is guilty for that name? Or how does this attraction depends on distance? Yes, yes, Coulomb law.
Yeah.
1 over r if it is energy, or 1 over r squared if it is a force, right? Good. But this lines, so this one looks like 1 over r, 1 over r. But by some reason, these lines do have minimum, right? It is what confused you and me. So it is not dropping down to infinity. It goes down as we approach and then goes up. Why does it go up?
Thought the covalent bonds like that.
Like why electron cannot smash into nuclei?
Oh,
Like why moon is not falling onto the Earth? They are attracting gravitationally similar.
it's a rotate. Rather
So and if it rotates,
they have a limit.
so that prevents it from falling.
Yeah.
So it's like one centripetal and another centrifugal. The force that is when you do a purification of chemicals in wet lab, you do centrifugation, right? So it's force outside. Same in the atom. So there is a attraction inside and repulsion outside. Okay? So if we cover these two concepts together, we will arrive to this conclusion. Whew. Basically, we got done. The rest will be just technical details. And those are energies. Minus 1/2, minus 1/8, times over 80. So when this negative moves around this positive on the circular orbit, you can characterize it with distance. Level of alert is orange, not red. Follow, but not with full strength. But be careful. If it moves, then it has velocity, right? Linear velocity. Velocity is derivative of position over time. Right? I'm not lying. That was right now. And if absolute value of radius stays the same, can we say that velocity is 0? It's a logical trap. If distance from nuclei to electron is constant, and velocity is derivative of position over time, distance is not changing. Does it mean that velocity is 0? Why? So it's vector, it's not just one number. Right? So subtraction of these two radii will be vector of velocity. Good, we are on the same page, and you all are past freshman physics. Now, if we have velocity at different instant of time, what will be the derivative of the velocity?
Acceleration.
Acceleration. Again, velocity will be constant if we are orbiting, right? And same trap. Velocity is constant, but acceleration will be not 0. Same vector rule, right? So velocity at this time minus velocity at this time in vector form. Okay. So it will be a little vector connecting these two arrows. Where this little vector connecting these two arrows will be directed to? Towards center. How will it be related to the radius vector? Huh? Opposite but collinear. Good. So these three are orthogonal to each other. And the acceleration of the object that moves on the circle is directing towards center. I'm always mixing these two words, but it's because I don't speak Latin. Centripetal means towards center, right? Otherwise, if there is no acceleration, like a rope or electrostatic attraction or like a disk of centrifuge, it will fly away. So that's only the reason why it doesn't fly away, the centripetal acceleration. Good? Yeah, good in time. And what is how can we quantify the time that takes for a particle to orbit one cycle? We can establish a ratio between linear velocity and arc length of the full circle, right? 2 pi radius and velocity. Will be period. And one of the period is frequency, right? And frequency times 2 pi will be angular frequency. It's not a surprise. Just silly definitions. Good? Still orange arrow. I'll tell you when it goes to the right. Now I will just show this exercise, but the next slide where it is typed. So I like it. Good. So you are experts in practical applications of complex calculus. In this course, you are continuously doing exponential with imaginary power and applying to different things. So it's not a surprise for you. You know how to deal with it. So what if we apply it to this little circling motion? Then radius is initial radius times exponential, where x and y will be projections of the radius on x and y axis. Make sense? If one projection is cosine, another is sine, it is perfect circle. Now, let's just practice what we did before. The derivative of the radius vector in respect to time. Since it is exponential, no one was objecting, which means it is correct. The imaginary unit and frequency comes up front, and exponential stays the same. Right? And you can skip the rest of it. Now, what if we apply, so this will be velocity, right? And this imaginary unit means I to the power of 90 degrees. So everything is shifted. Shifted by 90 degrees, it's like perpendicular, right? Perfect connection of geometry and complex variables. Now, if we take the derivative of velocity, the initial radius vector up front stays, imaginary constant and frequency stays, and then we take one more derivative of this exponential. And in the standard way, it brings us another power of omega and another imaginary unit. I times I will be negative 1, right? It's here. So we have negative 1 initial velocity and frequency squared. And then here we have the same stuff. It will be e to the power I omega t. Right? So if you combine together initial radius vector, R0, and the time-dependent part, you will get that acceleration is equal to radius vector with negative sign and multiplied by frequency squared. A little flash of red alert. Just notice this equation and make sure that you do not have conflict inside yourself about this. It seems natural, right? If I have a stone and a rope, I pull it always to myself. Maybe some words of a circle trajectory. Where do you see in real life? Just it's like 1 minute relax before we go to a really important thing. Where do you see the centripetal and centripetal forces in your everyday? Oh, making sharp turn. Okay, yes. Who never used a dishwashing machine? Yeah, other such people. So everyone used dishwasher machine. How does water comes in and out? In probably because there is pressure in the pipe. Why does it come out? So there is a pump, centrifugal pump. So there are like fins on a wheel that accelerate it and move it outside. So it's in every household. I have another example. So if you fly in space and want to stay on the space station for a long time, there will be some shortcomings for the human health. So there one needs to exercise much more than on the globe, otherwise it will be like bones will be fractured after return and muscles will like 50 times, or not 50, but 50% thinner. So it's without gravity, human body becomes weak very quick. But if one creates a space station that rotates, then this centrifugal acceleration will replace gravity. And then humans can stay in space like for the whole life without any shortcomings. So it is a big view with a center, and one can build a city there. Or one can, it's one of the projects for a station to be built next decade. So if it rotates, if it has the certain angle, then there are some numbers what should be radius and period of rotation to mimic the free fall gravitational acceleration on the Bohr. So it's like 22 feet, 2 revolutions per minute will be sufficient. Good. Okay, done with a little break. So now I have a very strict plan which can be shortened in words and delivered rather quickly, but there will be a few more slides. Suppose we have negatively charged electron, positively charged proton, and we do want to see, to quantify the centripetal, which is just Coulomb, and centrifugal force. We already got the acceleration, and it's not a problem to make it to the force. But why I will be investing generous 15 minutes? Because we are not starting this problem right now. We have a background of the whole course and at least 2 previous lectures. We know that if those are small quantum objects, the rotation are allowed to happen only with discrete values of angular momentum. And we are going to merge together the fact of discrete values of angular momentum and the practice of balance between centrifugal and centripetal force. Okay? So if you are happy with this idea, the rest are technical details. So, angular momentum. Then one can express the velocity and kinetic energy. Right now, we are not quantum theorists, but we are not classical. It's like semi-quantum, semi-classical. And it was first thing done by humankind to get this quantum nature, and now we are doing because it is like 20 times simpler than pure quantum consideration. So it's not operator in the full sense, it's kinetic energy. So mass velocity squared. And if velocity is expressed in terms of angular momentum, okay, so previous 2 lectures we were going from linear velocity to angular momentum. Now we are going back from angular momentum to velocity. It is angular momentum for radius and mass squared. And then we get kinetic energy is angular momentum squared to mass radius squared. Same as we did before. What is important? But we can look at this equation as function of distance. So, like I have a stone in a rope, but instead of a rope, it is maybe the elastic rubber band that can be longer or shorter. And I'm looking on the kinetic energy as function of distance. So the kinetic energy is inversely proportional to the radius and has always kinetic energy is positive. So, and it is proportional to the square of angular momentum, which is conserved. I'll make another comment, which is typically expanded long in the elementary physics books. Did anyone watch the figure skating? So there is an element when the skater picks up rotation and then pulls all hands nearby, and then rotation of the frequency of this rotation increases. So it is connected to this equation. If we keep angular momentum constant, we keep kinetic energy constant, and then depending on the distance, it will be quicker rotations. So propulsion. attraction, charge, distance, energy, natural constants. Right? It is what you used to see in SI units. And dielectric permittivity of spectrum, phi. This is good. This is correct. But I know myself as a champion of errors. Any additional constant in the equation gives a chance to make an error. What if we use a system of units where charge of electron and proton is measured not in coulomb, but in units of charge of electron? In such system of units, those will be just +1, -1. And if you design system of units where this constant will be equal to 1, basically then we will redesign atomic system of units where coulomb attraction will be just -1/r. And if you practice this atomic system of units, we just need to go into Google and find conversion. It's possible to derive personally, but it will be just wasted. There are standard conversions in atomic and SI units. So atomic units, mass of electron is 1, charge of electron is 1, Planck constant is 1, and 1/dielectric permittivity of electron is also 1. So it's a dream system of units. Very good time. Generous 12 minutes for the main part of the science on the Earth. So, even if we are not purely quantum, we are already instructed, we already got habit to think of energy as Hamiltonian and as a summation of kinetic and potential. Right? So we have kinetic, which is positive and inverse of R squared, and potential, which is negative and inverse of R. So potential energy makes more negative with the approach closer. Kinetic energy increases and becomes positive with the approach closer. Under the constraint that angular momentum is conserved, then it will be like the closer it comes, it gets more kinetic energy. So we will put index L because this is kinetic energy under the specific value of angular momentum. Plus term, repulsive, minus term, repulsive. A flash of red light. Just, it's a key point. We already agreed on fundamental concepts, and from mathematical point of view, this one is exactly what the rest are follow-up derivations. So, in case we do two fighting tendencies, and we know that solution is static. If electron is like revolving on a certain distance, nothing happens, it doesn't explode, there are no reactions. Philosophically, what does it mean? Neither one mechanism wins. They compete in equal measures. They come into equilibrium, right? Distance is assumed constant on a circular orbit. So the optimal way to think about it is that the electron that moves on a circular orbit experiences zero force, or centrifugal and centripetal forces are zero. But this one is energy, right? There is no requirement that energy will be zero. How can we get from energy to the force? What is work? Super. And work is energy. I like your thinking. Now, I invite everyone to follow leadership of Morgan. Work equals force times distance. So that's it. Now let's divide both parts from the distance. So what is force? Huh? Yeah, correct. But what is force if you accept leadership of Morgan?
Work divided by distance.
Yes, or energy divided by distance. Or if we are very picky and advanced calculus experts, it is derivative of energy over distance. Good? Super. So we are going to apply derivative over position to this equation. So if the derivative of this energy over position will be equal to 0, it means the two forces are equal to each other. Right? So we carefully apply this derivative, which is this part is constant. So here it is first derivative of 1 over r squared, and here is first derivative of 1 over r. Okay? So what happens with the derivative 1 over r squared? Power drops when taking derivative. So instead of -2, it becomes -3 this factor. What happens to power of here power -1? Becomes -2. Yes. Oh, it is good. So we are taking derivative of energy, and which means that we are computing. Before we were talking about energy, now we are talking about force. Centripetal, centrifugal. They are equal. Power 3 for a centrifuge, power 2 for a centripetal. Oh. Can we simplify this expression? So one can cancel r squared, 1 over r squared here and there. What are we going to get after canceling r squared here and there? Can we solve it for r? So we put r here, it will be distance will be equal to angular momentum squared over mass, right? You are making a discovery. It is a thing that is not in the intuitive thinking. The distance is a function of angular momentum. The quicker it rotates, the bigger is distance. Right? R equals angular momentum squared. The quicker it rotates, the bigger is the distance. And the angular momentum, I'm speaking it quickly, and there is no much words between these equations, but it is the core of our relation. So the distance is proportional to the square of angular momentum. And angular momentum is quantized. It is Planck constant times integer number. Right? So we can interpret it that if angular momentum is allowed to have only discrete values, then the distance between electron and nuclei is also allowed to take discrete values. And you derive it just by taking derivative of energy. So permitted distances, permitted radius of orbits are discrete. And this is not as important if we are doing ab initio computation or looking about chemical reactions, but all humankind was so excited and it was so simple to orbits of planets that people started drawing atoms as several planets rotating around nuclei. And they have very much different radii. But it is not a hypothesis. This is follow-up from quantized motion around the circle and from the balance between centrifugal and centripetal forces. So if angular momentum quantum number goes 1 to 3, then radius will go as 14916. Right? So they are substantially different. And we are coming closer to the image that was at target. So centripetal Coulomb attraction is negative, and centrifugal energy is repulsive. But depending on the value of angular momentum, it has different steepness. So we combine this line, black dashes, and thin red. And we are getting this long dashes. So at the limit of infinite distance, it tends to 0. At the limit of 0 distance, the repulsion wins and it goes to positive infinity. And in the middle, there is a minimum. And this minimum is where electron will sit. If we let nuclear distance from electron to nuclei to be a quantized value, there will be additional states here. But right now, it's just this distance. If angular momentum is bigger, then the centrifugal is this green, and we add black and green and get this dashes. And the distance will be bigger. So here is 1, here is 4. If angular momentum is 3, we add together this blue line and this black line, and we get 3. Or minimum, we get 9. So S, P, D, or principal quantum number 1, 2, 3. It's the same figure, just with zoomed in. And a summary that repulsive and attractive under condition of L squared, you give the energy. So if you plug in instead of R this value of L squared, then without drawing these figures, we will get centrifugal and centripetal. All distances are placed with angular momentum. Wherever needed, angular momentum is cancelled, and one gets this one factor plus 1/2, this minus 1. By subtracting minus half, or plus 1/2 minus 1 will be minus 1/2, and it will be 1 over L squared. Okay. So progression of states is starts from negative value and then goes up. Almost. So in atomic units, the energies of the states will be minus 1/2, minus 1/8, minus 18. Right? And if we go into experiment, this minus 1/2 in atomic units will be minus 13.6 in electron volts. Next one will be minus 3.4. The transitions between the states is what happens on experiment, what absorbs or emits. So all of these discrete values. So different orbitals, and for transitions between different orbitals, there are different wavelengths and frequencies of radiation. The from ground state to any excited will be in ultraviolet. It's called alignment, and it is not seen. From the first excited to other excited, it's called Bohr, and it is invisible range. So it is what humans can see use a simple experimental tool. And if you want to do a spectrometer at home, just do a tube with high voltage and hydrogen in dark room, slit, prism, and it's possible. One doesn't need to be in a highly expensive equipped lab to see these lines. And this will be Balmer series. This will be transitions from first excited to other excited states. Line, and not continuous spectrum. Thank you for your questions. Meeting is done. Happy Thanksgiving. Thank you. Oh, any questions? Feel free to ask. I will stay here.
Did he finish this?